Good evening, everyone, and welcome to day 5 of online class in physics. I'm just going to go through a few things really quickly. Number one, if you are not reading the stream, I would encourage you to do so as I have extended the date for your light CER. That's why it's not reflected in the gradebook quite yet. And also have provided some guidelines. Note that just follow the guidelines. Read through this, please. Other than that, the polarization and color assignment, I had a great job reading you guys. I just haven't gotten quite back to providing feedback yet, and I will get that back to you shortly. So, a couple things for today. Number one, we are finishing up our waves unit. Unfortunately, we had to cut a bunch of things out that normally would have been easier to do in class, including several of our labs, everything on lenses. So I know that you missed that. I'm sorry. And also some of our application assignments that we were going to do. But at least you now know this is over. For those of you who are keeping track, we have about a month and a half, I would say. About a month and a half of school left. For those of you who are not seniors, we're going to wrap this up with about a week and a half on gravity. So we'll start that this week also and go into next week. And then after that, we will finish up with electricity, of which there are bunches of applications. And you guys have had this unit before in physical science and chemistry, so it will not be too intense, okay? So let's go ahead and dive right into this assignment. I've only got 2 slides to go over with you, and they're both about today's assignment to review back to. Please make sure you're checking out the PowerPoint. It is right here, and I will give you guys a new one once we get to gravity. Alrighty, so number one, you have a step-by-step thing over here. There are links, including to the Google form, which I'm using for your attendance assignment. So if we go here is your exit ticket, your name, your class period, a couple questions about the assignments, and one question for just reflection. Just how are you guys doing? Okay, after that, here are the links to which to navigate to. I have these on the handout also, and then how to complete the handout. So let's go into this. So last week, we talked a lot about color in particular. And a few of you had some questions, so I thought I would go over those really quickly. Number one, the difference between the additive primary colors and subtractive primary colors. So the additive primary colors are red, green, and blue. I talked about how these are the colors of light that your eyes actually see and process. This is a combination of light of different wavelengths. Once you have all the wavelengths, you combine to form white light, which is not necessarily color in itself, but white light can be refracted into the rainbow, into all of the colors. So if I see red light, so this would be like a red light shining at you, then that light is red because it emits waves that match the same frequencies as red on the electromagnetic spectrum. Now, this is how different technologies like pixels and screens work, right? This is when we're talking about what your camera looks like, what your screen looks like right now, how movie theaters work to get you the best picture. We're talking about additive light colors. Now, subtractive light colors are what you're probably a little bit more familiar with. These are your classic red, blue, yellow, or in this case, it's actually yellow, cyan, and magenta, are going to combine because they are pigments. These colors add together to make black. And if you've ever taken a bunch of different pigments together and just mix them all on a plate, you got like a brownish black color. So what's the difference between these two things? In this case, the light itself is that color. It emits red light. In this case, this red right here, this red pigment is red because it is reflecting red light back to your eye. It's actually absorbing everything except red. So this is how we know what we see. So if we look at why leaves are green, for example, The leaves are green because they can't absorb that wavelength. It actually doesn't work very well for them. They absorb some of it, but they prefer other frequency of wavelengths in the blue to violet spectrum and also in the red spectrum. And because of that, because green isn't that useful of a wavelength for them, they go ahead and they reflect that green light back. They're like, just get rid of it. It's not important. And because of that, everything that does photosynthesis looks green to us, even though to the plant, green is kind of a garbage color. So there you go. Green is garbage. All right. The second part of your assignment is to do with wave particle duality of light. And we're going to look at the most classic experiment of this, which is the Young's double slit experiment. I have you guys just kind of describing how this experiment went. Real quick, so a couple things. In this experiment, remember that people were very, very divided in actually a very heated way over whether or not light was a particle or a wave. A lot of people thought it was a particle, including Newton. Once Newton said something, pretty much it was taken as an actual fact, which is kind of understandable. It's like Einstein, right? Like if Einstein said something and someone else like came to you and they're like, oh no, this is wrong, you would be like, no, Einstein said so bye. So this was kind of the same way. So Young came around, brilliant mathematician, and was like, okay, well, I'm going to prove that it can act like a wave, and hopefully that will shut up some of the haters. So what Young did is he took a light source and he shined. That light source entered two very, very narrow slits in this sort of fabric type thing. And what you would expect is that if light acts like a particle, then the only thing you should see are two bands of light, right? You should see a little bright dot here and a little bright dot here. However, because light can also act as a wave, you see a different pattern. You see constructive and destructive interference. So remember, when describing waves, interference is when waves can stack on top of each other. They can interfere with each other. And this looks like if it's constructive, then they're adding together. So we see here, these two waves from this light source and this light source are adding together, right? They're adding together. And on our actual, like if we were to look into this viewer, we would see a bright spot right here, a bright band. Here, we see that they're still overlapping. However, they're overlapping in opposite directions. Notice how this crest and this crest are in opposite directions, right? This one's going up, this one's going down, so on and so forth. So if we put these two on top of each other, they cancel each other out, and we have destructive interference, which shows us a dark pattern. So we would just see bands of bright lights all in a row. Okay, so quick summary: if a light is a particle, you can read this for yourself. I won't read it too. And also, I have a short and quick video here. It's by Verisadium, which I really like. The guys go around and they ask people, mostly I think from Australia, maybe it's New Zealand. I'd have to double check. And they ask them some basic questions about physics. We've watched a couple of these since we were talking about motion and forces. They're pretty fun. They make you feel good about your schooling system here. Yay. And also, they do a really good job of setting up this experiment themselves and showing you what that would have looked like if we were able to build it in class, which we had planned on, but I'm sorry. So let's go ahead and look at your actual assignment. All right, so number one, you all have this copy. Okay, I've put a link here to read over Young's experiment in greater detail. Oh, let's go ahead and fix that. If you haven't downloaded Grammarly for whatever reason, it's free and it catches a ton of grammar mistakes that are super easy to make. Better than spell check, so look into that. Okay, So here's the link here, and we're going to go right here to Young's Experiment Interactive. Here's where this first page is just it explaining how the interaction works, what you guys are actually doing. Conceptual analysis. As this one variable changes in the interactive, how does the second variable change? Does it increase, decrease, or remain the same? You can do a couple things here. You can just bold that. I don't know if that's the answer. I'm just bolding one to show you. And then remove that, please. Remove the rest of it. Or if you just bold and underline the correct answer, you want to even like go a step forward further, just go ahead and highlight that sucker. Just let me know what you think is the correct answer. Okay, so that's what you're doing on questions 1, 2, and 3. They just ask you, hey, what's the relationship between these variables? Then there's one more interactive. It's super easy though. We will go to that one in a second. All right, so let's go ahead and go to the Young's interactive. Yay, it's physics classroom. This is my favorite. Okay, so there's a couple things that you can do here. Number one, this is a laser. It is shining different types of light. Let's go ahead and hide this. All right, so I'm going to start it off on red. Don't worry about moving this yet. That is a different part of this interactive in which we were going to calculate the wavelength of that frequency using an equation. However, this thing is super finicky about significant figures. And also, yeah, it's just really hard to teach more advanced math over the computer. So no, we're just going to describe it qualitatively. So number one, you can change the width between the two slits. So notice there are two slits here. You tap here to make those wider. That is one of the variables you are going to change. Number two, you can drag this away from you or closer to this. Now notice that whenever I change these things, let's make that pretty small, and there we go. Okay, then what you're actually changing are the interference patterns. So down here, I have the centimeters between the patterns. So the brighter spots, like I'd say probably the brightest spots are these three, right? These are the three sides of the most constructive interference. This is both of those wavelengths adding up together to form a brighter band. To the sides where you see just darkness, the darkness in between spaces, that is the destructive interference that is occurring between those two light sources. Okay. In this, you were just describing how varying the width between the slits, the distance from the screen to this guy right here, how that changes the interference pattern. Okay. Let's see. All right. Okay, and again, this kind of describes all of that for you. Actually, you're not doing this part, so let's just get rid of it. Okay, there we go. Alrighty. Yeah, and they describe what those are. So the distance between the bright bands, that would be how does changing this change the distance from this one on the far left to this one on the far right as I get further away or closer together. How does the distance between this band and this band change? Okay, moving right along. The next one is just a small quick thing on color addition. Just really drive this point home here. Okay, here's our interactive. You have a couple different ways you can interact with this, but for right now, I'm just going to keep it simple. If you're super interested, you can upload your own pictures and see what the color breakdown of those looks like. So yeah, you just have three different sources of light. You can add them together and form different colors as you will. Let's see, we make this color, and this color. Okay. Doing this, I gave you guys a thing. So let's say that we want to make like a banana yellow, then I would say a banana yellow is pretty close to, what if I made it? It's a little too bright. That looks like a non-ripe banana. There we go. So in your actual assignment, you have a list of objects with different color intensities. I just want you to play around with it and put approximately the right percentage, which would create a new color. So here I would say banana yellow, which is kind of a less bright yellow, sort of a dullish yellow. This is what bananas should look like. If they're too green, then you're doing it wrong. Is about 88% green and 98% red and 0% blue. We don't want any blue in that sucker. So if I scroll down here, I gave you a few different objects or different things like ink or an orange that you would eat, a different flower, a school bus, forest green, navy blue. I realize that this is objective, right? Colors look slightly different to a lot of different people. Not necessarily each of us, there's not that much of a gender difference, but a part of it exists. Therefore, there are no correct percentages. Just make sure you are filling it out in such a way that makes sense. For example, if you were to tell me that cyan sky is 80% red and 20% green, then that's probably not correct. You should check that. And then also if you want to come up with two of your own. So pick something around your room. Tell me what that object is. If you wanted to match the color of that object, or if you wanted to match the color of the paint or pigment of your walls, then what combination of these three types of light would give you that? Okay, and that is it for today's assignment. We will start back on Wednesday and Thursday with our introduction to universal gravitation. Thank you.